Previously, we built a typical model for distribution optimization. In the field of optimization research, we named the problem the vehicle routing problem. That's VRP for short. There are many ways to solve VRP, which mainly can be classified into two types: exact algorithms and heuristic algorithms. Exact algorithms can solve the problem to optimal. The common exact algorithms include branch and bound approach, cutting planes approach, network flow approach, dynamic programming approach, and other unlisted approaches. Since VRP is NP-hard, exact algorithms for middle and larger size VRP problems are always not efficient. So heuristic algorithms are exploited to obtain near-optimized solutions. Heuristic algorithms for VRP usually contain these three types. We will roughly present all these algorithms and introduce one or two of them in detail. Before presenting the exact algorithms, you should know that you could use these optimization softwares to obtain optimal solutions. But you can get the results in reasonable time only for limited-sized problems. Okay, let's start with branch and bound algorithms. Last course, we talked about the key idea is iterative two steps: branching to divide the feasible region and bounding to find an optimistic evaluation of the region. For VRP, we generally relax it into several travel salesman problems. That's the classical TSP. In TSP, the decision variable is a binary variable, which denotes whether or not I and j is linked or not. We marked as xij. So for each subproblem, TSP, you can choose one of the xij and take 1 or 0 to branch it, and bound to find an optimistic evaluation. Then continue branching and bounding on the same branch or go to the upper level of the tree. The objective is to minimize the total cost of all TSPs. So the basic idea of cutting planes approach is roughly the same as the branch and bound method. That is, firstly, solve the corresponding linear programming without considering the integration constraint of the variables. Stop operating if integer optimal solution is obtained. Otherwise, if the obtained optimal solution does not meet the integer constraint, then new constraint is added to solve the problem again, which is to cut off some non-integer solutions of the relaxation problem and keep all integer solutions. So the newly added constraint is called the cutting planes. Network flow approach is an approach to study optimization problems on a network in graph theory. A network is a connected weighted directed graph D equals to VEC, in which V is the set of vertices containing a start and an end point, E is the set of directed edges, and C is the capacity on the arcs. The flow on the network is feasible flow from the start point to the end point, which is non-negative and under capacity constraints. Additionally, except for the starting and ending point, it is required to keep the inflow and outflow in balance at all halfway points. Take this graph as an example. If this is a road network, the vertices are cities, weights on arcs are distances. The problem is which route should be chosen to transport freights from point S to point T to minimize the total transportation distance. Such a problem is the shortest path problem. If this is a pipeline network, then weights on arcs are maximal pipe throughputs. The problem is how to arrange the transportation line to maximize the total transportation from point S to point T. Such a problem is a max flow problem. So dynamic programming is a systematic technique for solving multi-stage decision problems. The basic idea of dynamic programming algorithm is to decompose the problem into several subproblems, or say stages, and solve the substages sequentially. So the solution of the former stage provides useful information for next stages. For a subproblem or in a stage, list a variety of possible local solutions and return those that are likely to reach the optimal solution by decision, while discard other local solutions. The solution of the last stage is exactly the solution to the initial problem. So, in general, exact algorithms are based on strict mathematical approaches, and their solutions are usually superior to artificial intelligence algorithms when they can be solved. But due to the strictness of mathematical method, it is usually unable to avoid explanation explosion. So, the exact algorithm can effectively solve the small and the middle-sized VRP. But for larger-sized problems, their application is very limited. That's why heuristic algorithms are proposed and explored.